speaker is Ming Yi from Rice. Ming is going to tell us about Bismuth Halides, a quasi-1D platform for novel topological states. Please take over, Ming. You may want to swap the display. Now we are looking at, right, looks good.
Okay, thank you very much, Mengke. Thank you very much, Mengke. And I'm also very grateful to have this opportunity to tell you about our experimental exploration into this really fantastic system. So I'm very glad I'm following Fan's talk, where he already very nicely introduced all the theoretical background motivation for studying this series of compounds, and let me show you what we have done experimentally. Oops. Okay. So this is not possible without this really nice collaboration with this group of people from whom I've really learned a lot from this project. The photo emission work I'm going to show you is done in collaboration with Bob Birgeneau's group at Berkeley with our joint postdoc G-sub-O. And the theory is with Fan Zhang's group at UT Dallas. The beautiful single crystals are grown from Bing Liu's group at UT Dallas, and also a quantum transport collaboration with Jinyi Liao's group at Ohio State. The ARPES measurements is really carried forward by the two fantastic postdocs here, G-sub-O, and also Jianwei Huang, who is our postdoc here at Rice, who have been really good mentors to all of our students. And the measurements are enabled by the advanced beamlines at SSRL and also beamline 7 at the ALS. And then the first principle calculations are in collaboration with Chao Lei at UT Austin. And everything I'm going to tell you today are described in these two manuscripts, one of which is published, the other one is forthcoming. So I'm glad I don't have to really deal with to introduce again the theoretical background, but just for completeness, let me just state that tracing back to the original proposal for TI in 2D, we know that we can use a single Z2 topological invariant to explain a gapless boundary mode surrounding a 2D insulating state. And when we extend this to the 3D, we are now introduced with a distinction between a weak TI and also strong TI. And the distinction is that for weak TI, we only observe even number of direct crossings on selected surfaces of the crystal, whereas for strong TI, we expect to have odd numbers of surface direct cones on every single surface. And the naming convention for a weak TI is because originally it was conceived that the topological states in the weak TI is quite fragile, because you can imagine if you have even numbers of direct cones under some sort of perturbation, such as disorder or dimerization, you can easily gap out the topological surface states, which makes it indistinguishable from a trivial insulator. But now, of course, due to all the great work in theory, we now understand that this sensitivity, shall we say, is actually a benefit, because this makes the weak TI systems much more tunable, and for realizing, for example, higher order TIs. So it's really interesting to look for systems that are weak TI. And as Fan has already introduced, in experimentally, the vast majority of compounds that we have identified as TIs are the strong TI, and it's really difficult and challenging experimentally to identify weak TIs because of following reasons. So if you consider there are different routes to realizing a weak TI, one way is to stack weakly coupled quantum small Hall insulators, where the gapless boundary modes can then couple together to form these topological side surfaces. But then experimentally, it's difficult to actually confirm that these are actual weak TI, because that means these samples are very hard to cleave on the side, which makes them not really accessible to probes like STM or ARPES. So this is an example. There has been very nice work done in this field, but you can see this is one demonstration where we can only see the topological Dart 001 surface. The other route is by hydrostructural engineering, and here one runs into the issue that it requires fine-tuning of intra and inter-layer coupling to obtain the two-band inversions we need for the weak TI. And you can imagine that is also hard to realize experimentally. So this is why we were, as Fan already described, why many groups are attracted to Quasi-1D materials because as demonstrated by the Bismuth Halides, because they're weakly coupled chains, that means two things. One is that you can realize really a variety of stackings that can give us different types of novel topological states. And then practically, when they're weakly coupled chains, that means we can easily cleave different surfaces and therefore actually look at a surface-dependent measurement of the topological surface states. So forgive me for not being very complete, but there are numerous groups working in the Bismuth Halides, and this is an incomplete list of the groups that are working on this type of materials. And this is just demonstrate what a rich system these are. So I'm going to tell you about our contribution in this regime. And so our collaborator Bing Liu's group at UT Dallas, they have very nicely grown these beautiful large single crystals, and you can see these are single crystals of bismuth iodine, and they have very shiny and flat large surfaces, both on the top 001 surface and also on the side 100, which means that we can actually glue the samples with different orientations and then cleave them and to expose large measurable surfaces with just standard regular ARPES with, say, a beam slot of 50 microns or so. And not only that, they're cleavable, they're also exfoliable, which means they're gateable, and then also they're soft, so they're strainable. So these are really largely tunable systems for realizing different types of topological states. What's also interesting is that this consists of these bismuth halide chains, which are like Lego blocks, and you can stack them in different ways, and different types of stacking give us different symmetries and therefore different topological states. And so in Fan's very nice archive paper, they discuss the different types of stacking of these chains, and here are the three most common ones that they laid out. And the simplest one is, of course, just with A stacking, so every layer is the same. And then the unicell is a single layer of bismuth halide chains. And then we can also have, a dimerization realized in two types of stacking: AA prime stacking, where there's some sort of small shift. So the unicell, the basic unicell, consists of two blocks. Or you can have what's called AB stacking, where every other layer is flipped 180 degrees. And as Fan also demonstrated, these two actually would give you different types of inversion centers. I'm going to come back and discuss this later. But let me first demonstrate from full emission what we find with the simplest stacking, which is just the pure single block A stacking phase of the bismuth halides. So here, as Fan has also already demonstrated, if you carried out first principle calculations, very beautifully, these materials have a nice band gap, bulk band gap around the Fermion level, if you don't include spin orbit coupling. And there's spatial inversion symmetry, there's 010 mirrors reflection symmetry, and also when we start to include spin orbit coupling, and we can see that you can realize one of a couple different states. Depending on the size of the bulk gap at different momentum points, you can have the situation shown on top. Here, you can see with this kind of a bulk gap, you can have a single band inversion in the bulk states. And what that means is that, if this is the Brion zone, if you have a single band inversion, and if we project it to different surfaces, we will have a single direct cone on each of these surfaces, and that will qualify this phase as a strong TI. Or you can slightly tune the size of these bulk gaps at different momentum points, which is demonstrated on the bottom row. Here we can realize two band inversions, and when you have two band inversions, as Fan's already nicely shown, they would annihilate when projected to the top surface, and they will give you two direct cones on the side surface, and therefore this will give us a weak TI. So you can see that the bismuth halides are actually at the boundary between where you can perhaps find a strong TI or a weak TI. And therefore, this is really an interesting system to really experimentally identify what is the topological nature. So in actual crystals, the first known member with the simple A stacking is the beta phase of the bismuth iodine. And this has already been done by a number of groups, but this is our measurement with our collaborator Bing Liu's group. And here, when they see from single crystal actual diffraction, they can see that there's a natural lattice distortion around 300 Kelvin at room temperature, above which the crystal shows unicell of a single layer. And this is the beta phase. This is simplest stacking order. And then when you go below this transition, which is the first order transition shown with the hysteretic behavior, there's additional diffraction spots, which indicates that now the unicell has doubled. And this is the alpha phase. And I'm going to come back and talk about this later. But let's first talk about the simplest scenario of a single block, single layer phase of the beta phase, and what does ARPES observe as a topological state? So we were, of course, now the ARPES results on this, and there's been a controversy in the literature regarding bismuth iodine, with one paper reporting a strong TI phase, and then this is Takeshi's very nice paper showing that there's that it's a weak TI using nano ARPES. So here we wanted to observe for ourselves what really is the topological state of the beta phase of bismuth iodine. And because of the very nice large single crystals that we obtained from Bing's group, we were able to directly measure and distinguish the 100 surface from the 001 surface just with regular ARPES. And you can see that the Fermi surface measured on the 001 surface have bright spots, whereas for the 100 surface has this one-dimensional feature, right? So they're distinct. And not only that, we can also look in the energy dimension by taking a cut, and you can look at the periodicity of the bands. And from the periodicity, we can match that to the inverse of the lattice constant along different directions and confirm that indeed this one is coming from the 001 surface. And this quasi-1D Fermi surface is associated with the 100 side surface. Okay, so given this way to distinguish what surface we're measuring, we can then take a look at what is the topological nature of these different surfaces. So this is work done by Jianwei, published here. So let's start with the top surface, 001. We have these bright spots in the Fermi surface. If we take two cuts, you can see that they both show hole-like bands with the band top. And then the gamma point, there's a large gap. And then at the side, on the side of the Brion zone, we have a much smaller gap. What are these states? Well, we can vary the photon energy to probe that the KZ dimension of these bands. And from that KZ dependence, we can see that the band top here, we can focus around here and then vary the photon energy. We can see the band top here actually varies periodically with photon energy. That will indicate that this is a bulk band because surface states won't disperse along KZ. So we know that these two hole bands are bulk bands. Furthermore, we want to also look at, close to the Fermi level, what is the situation there? Because these are, again, measured above room temperature, a very high temperature to look at the beta phase. We can use thermal population to look at the bands above the Fermi level. And here you can already see, and this is the bottom of the conduction band. If you zoom in and look at the EDCs, you can clearly make out that there's a gap here, and this is the bulk band gap. So we can see that on the top surface, 001 surface, there's no topological surface states. There's only a bulk band gap, which straddles the Fermi level. Okay. So now, next we want to look at the side surface, which is a more interesting one. And on the 100 surface, if we take a look at the band dispersions here in the middle on the side, we can see that, again, I won't go into details, but these are actually the bulk bands. And then within the bulk gap, you can see here are the surface states, surface direct crossings. And if we look at the EDCs here, we can see that the surface bands actually is consistent. This is where in the middle of the band, we can see that this is consistent with the gapless surface state. So we can understand that, therefore, we observe two direct surface states on the side 100 surface, and nothing, no topological surface states on the top. And this would qualify this as a weak TI. So here, this is consistent with this expectation of two band inversions, which is consistent with the identification of a weak TI for the beta phase of bismuth iodine. This is all very nice and very cool. But the problem, there's one disadvantage of this, which is that everything I've shown you so far was taken above room temperature. That means that this is actually really difficult to characterize the details of topological surface states or use them or look at them in fine features. But what we really desire is some sort of a stable weak TI that is stable over a large temperature range down to the lowest temperature, where we can actually do stuff with it and look at it carefully and study its from the surface and band dispersions and so on and so forth. So how do we do that? We want a stable beta phase down to low temperature. So Bing's group and Fan's group work together very hard to actually identify that if you substitute on the iodine site with bromine at some ratio, you can actually realize a very stable beta phase at all temperatures down to the lowest temperature they can measure. So to demonstrate that, you can see the contrasting transport behavior. So bismuth iodine, you see this first order transition that separates the beta phase and the alpha phase. In this 2.8 amount of bismuth bromine there's no transition, and they have also confirmed this with single crystal XRD to show that this is really a stable beta phase down to low temperature. And from first principle DFT calculations, we do see that there are two band inversions at both the L point and N point. That's the stage that we expect a WTI for this stable beta phase. To demonstrate this experimentally, work carried out by G-Soap, he measured independently the top 001 surface and the side 100 surface. And again, you see the very distinguishable Fermi surface topology. So here on the top surface, we have the bright spots. On the side surface, we have the Quasi-1D features. This is consistent with the beta phase of the bismuth iodine. Next, let's go through in detail what is topological nature. So on the top surface, 001 surface, again we can see beautiful whole band top. These are bulk bands, and they are bulk bands. Again, we can show this by varying the photon energy. This is the top of this whole band, and you can see that varies periodically in KZ, which demonstrate this is a bulk band. And furthermore, we can also fit the size of the bulk gap by taking individual EDCs here. And this shows us that the bulk gap varies from 195 millivolts to 210 millivolts, right? So that tells us the minimum size of this bulk gap is larger than 100, it's almost 200 millivolts. And within this gap, there is no topological surface that we observe. Okay, next, let's look at the side surface. The side surface here, we can see that, again, in like at the gamma point, also at the Z point, there are very clear direct crossings. And if we zoom in, we can make out exactly the energy where the direct crossing occurs, 110 millivolts, 140 millivolts below the Fermi level. Now, what's interesting is that these two direct points, not only do they live within the bulk gap of the 100 side surface, but they also live within the bulk gap of the top 001 surface. That means that here in this energy window, there's no other bulk states anywhere in the crystal, and all that's left are these topological surface states, the two direct cones, a very clean and simple electronic structure. So given this measurement, we can actually, and also they live quite close to the Fermi level. So you can imagine they will be susceptible to doping to bring them to the Fermi level. So given the experimentally observed location of these direct crossings, we can then work with Fan's group to work out the minimal, simplest effective Hamiltonian that respects the symmetries of the system to come up with this prescription of the surface state. So if we have the two direct crossings, that means that we will have this kind of set of surface states that includes, in addition to the two direct crossings, also two sets of Van singularities here. And I just want to mention that we can identify location of these based on the measured location of direct cones, and also the measured Fermi velocity of these direct cones. And these Van singularities, because these Van singularities are surface states, they have divergent density of states, as shown here. And Fan has already indicated that this will mean that this would give a host of very interesting Lifshitz transitions, and which is shown here. So let me try to walk you through this. given this kind of structure, let me first start with close to the Fermi level from high on top. So if we're at this energy, we will have this kind of Fermi surface, which has a large open Fermi surface with almost quasi-1D dispersions, which is the electron light here. If we go down in energy, the first lift transition occurs at the energy of the top pair of Van Hoff singularities, and this is where this large pocket gets pinched into three electron pockets. And then if we go further, the next interesting energy is the top Dirac point at the gamma point, and this is when the pair of electron pockets here change into whole character. So if you go down, you can also go down to an energy where the Fermi pockets of the whole pockets and the electron pockets are gave rise to very good nesting conditions. And you can imagine this would be a really interesting regime to look for any nesting-driven instabilities. Keep going down. The next energy that's interesting is the lower Dirac point. This is when the center electron pocket changes character into whole. And then the next energy is the bottom pair of Van Hoff singularities, and this is when the three pockets merge together and then eventually become a single open large hole pocket, which is the reverse of the initial electron surface. So this shows that this kind of surface topological surface state topology, it will be very interesting because we can give rise to a number of lifted transitions, and not only that, experimentally this would be feasible because these features are completely exposed within a global band gap, which means that they will be accessible by transport, by STM and other probes. And furthermore, they live really, really close to the Fermi level, and you can imagine with electrostatic gating or chemical doping, one can at least achieve. It's feasible to achieve the doping of the system to realize these types of evolution. So experimentally, we can also cut at different energies to see that the constant energy contours indeed is consistent with the warping produced by this model. So here, then therefore, we really think this iodine 1.2 and bromine 2.8 is an ideal weak TI because it's stable over all temperature scales that we can observe, and the topological surface states is completely exposed. And there's also there's a number of interesting energies where we can feasibly tune by gating or doping to make to the Fermi level to really look for this exotic many-body physics, as Fan has already demonstrated. Okay, so that everything I've discussed so far pertains to the simple A stacking with a single unit cell. Now is the more interesting case where we can look at what happens when we dimerize them by different types of stacking. And so, and all of this is really hinges on the understanding that the weak TI phase of the beta phase of bismuth iodine can be understood if one could state as a stacking of these single layer of quantum Hall insulators, which Fan has already demonstrated here and also mentioned by different groups. And I think of the talk after the next talk, we'll discuss this in more detail. But with this kind of building block, one can think about realizing higher order TIs, which I don't think I need to introduce again, since Fan has already very nicely demonstrated. But beyond the first order TI, if one finds a way to gap out the topological surface states of a 3D crystal, one can have a situation where we realize hinge states living in a gapped surface state, living in the gapped bulk state. And this will be a second order TI. And then furthermore, if we find a way to gap the hinge states, then we can get to the third order TI where we have corner modes. So I'm going to show you then I'm thankful that I'm following Fan because here I also have just recapture what he has already motivated. We can understand the pathway to generating a second order higher order TI from the SSH model, where a half filling one can have dimerization, but there are two ground states, one of which will leave edge modes here. And so carry this analogy to the Bismuth halide systems that we have here. We can think about each layer as one of these dots. And if we realize some sort of, in the simplest case of no dimerization, as Fan has already patiently explained, there's inversion center, which indicates that you have edge modes on the two edges. But if we introduce dimerization, there are two ways to dimerize this. We can have a situation where the inversion center is in between the layers, in which case the dimerization on the left-hand side and the right-hand side are exactly the same. Or we can have the inversion centers within the planes. In that case, there's an offset between the dimerization on the left-hand side and the right-hand side. And there's a distinction between these two types of dimerization. But these two types of dimerization can be realized in the AA prime stacking and the AP stacking. More specifically, in the alpha phase of bismuth iodide, this would be consistent with this kind of dimerization, while the alpha phase of a bismuth bromide is consistent with this kind of dimerization. So just to be more complete, so for the alpha phase of bismuth bromide, where the inversion centers are within the planes, no matter how you terminate this, the four types of termination combinations on top and bottom, you will always have edge states. So therefore, the alpha phase of bismuth bromide is intrinsic high order TI. And in contrast, for the case where the inversion center is within the two layers, there's one situation out of the four, where if you terminate of even layers, you will have no edge modes, but for the three cases of the four combinations of terminations, you can imagine you will end up with edge states. And in a real crystal, in a real experiment on the cleave surface, you're bound to have probably combinations of these different terminations, and therefore like the presence of hinge states. But that will depend on the number of layers here. And so therefore, the alpha phase of bismuth iodide is termed extrinsic high order TI. So experimentally, what do we see? And the most simple way to look for this dimerization is actually given to us naturally by nature, because in bismuth iodide, at 300 Kelvin, this lattice distortion would double the unit cell. You can see that in additional spots here. And so remember the beta phase we have already gone over. This is the weak TI phase. So now I'm going to show you what do we see experimentally for this across this thermal transition into the alpha phase. So first, let's look at the simpler single layer beta phase high temperature. This is the calculated KZ integrated bulk band dispersions for the beta phase. And you can see side-by-side comparison with our measurements at 330 Kelvin, and they are basically a very good match between left and right. And this is because of the KZ broadening that we have intrinsically in photon emission. Now, if we do the same calculation for the alpha phase, you expect that when you double the unit cell in real space, you fold the Brownian zone in momentum space, which means the bands would double. And this doubling of the bands is very clear in the calculation, and also very clear in our experiment. So here we point out the splitting with the pairs of arrows, and hope you can see that this is probably the clearest situation, but you can see the doubling of the bands consistent with the calculation, which indicates that the electronic structure indeed follows the unit cell doubling. So that's a good thing. Having confirmed that, we want to look for this transition across the transition, close to where this transition actually happens around 300 Kelvin. Unfortunately, at 300 Kelvin, there's a lot of thermal broadening, which means that it's hard to actually absolutely resolve the two separate bands. However, even though we cannot resolve the splitting of the two bands at that high temperature, we can see that when the bands double, you expect that this peak will broaden, right? So with that, we can follow, for example, trace the horizontal cut here, this energy. And these two peaks here are shown here, and you can see that across this transition around 300 Kelvin, you can clearly see the width of this peak actually become sharper as you go to higher temperature. This is definitely not thermal effect. This is consistent with the transition from a two-layer unit cell to a single-layer unit cell. And then we can also capture the hysteretic behavior of this first-order transition by warming up and cooling down. And that his erratic behavior is really consistent with the resistivity measurements shown here. So just to quantify this, we can fit the width of these peaks as a function of temperature. And for the warm up and cool down, you can capture that there's a jump in the full width half max. And that's consistent with the resistivity measurement. So this indicates indeed our sample goes through this band doubling effect. Okay, so having established that, we want to look at what happens to topology here. So I've already shown you what we see from the beta phase here. This is from the topologically dark 001 surface. These are the pair of direct crossings from the 100 surface within the bulk gap. Now, when we go to the alpha phase, actually, if you zoom out from very far away, you hardly see any difference between the two, except perhaps if you look at, you know where to look, you can see the band doubling effect as seen here, for example. But the feature is actually quite subtle. If we zoom in, I guess this is the point I should probably mention, that this is where we differ from the earlier report last year showing that the alpha phase of bismuth iodine is topologically trivial with very different fermiology, but here we see that they actually show quite similar Fermi surface topologies between the beta phase and alpha phase. Furthermore, we want to look at what happens to topology. So if we look at first on the trivial 001 surface here, zoom in here to this bulk band gap, the bulk band gap remains after the band doubling, so nothing changes in topology here. But the interesting thing is that if we look at the 100 surface where the direct points reside, what's interesting is that while they are gapless in the beta phase, we do observe very clearly the opening of a gap in the topological surface state. So this is actually really consistent with understanding of the behavior of a second order TI, which means that due to the dimerization of the crystal, we have a opening of the gap in the surface states, and we expect that within the surface state, there should live the hinge states. And from full emission, this is really difficult to resolve to that fine spatial to look at the edges. But at least what we can resolve is the gap bulk state and the gap surface states, which would be consistent with the understanding that the alpha phase of the bismuth iodine is actually a second order TI. Okay, and then also furthermore, we have demonstrated from temperature dependence that this is naturally given at room temperature, the topological transition between a weak TI and also a higher order TI, naturally given in bismuth iodine. Okay, so I think I'm near the end of my talk. I showed you really very interesting platform in the bismuth halides, and we studied this topological phase transition in bismuth iodine. I also showed you our understanding of our finding of the bismuth iodine bromide system as an ideal weak TI with a host of very interesting exotic physics to be realized. And I didn't have time to show you, but we also recently measured bismuth bromide, which is consistent with it being a high order TI. And I really hope I can convince you that experimentally, this is really a fantastic system to study because not only because of the tunability, but it's electronically very clean. The topological states are really exposed in the bulk band gap, living really close to the Fermi level. And because they're exfoliable, they're also gettable potentially to realize all this range of many body physics that Fan has already touched upon. So we hope that in the future we can come back and update you with more interesting realizations of these effects. So thank you very much.
Thank you, Ming, for the fantastic talk and very interesting result. And now we open for the questions. See if we have anyone from the audience.
I have a question on page number 23.
23.
In the meantime, I would like to say it was a really interesting talk, Dr. Ming.
Oh, thank you.
Yeah, and here on the bottom row, so on the left side and the extremes, we are able to understand that judging by the bulge, one can be electron, the other can be hole. But in the central part at minus 125 milli electron volt, how are you able to judge that center one is electron and the top two are top and bottom are hole? That part I not able to understand.
I see. Thank you, Nico. Thank you for your beautiful crystals. So based on the location of the two direct cones that we observe at the gamma point and the Z point, that means that consistent with the symmetry of the crystals, we necessarily have this kind of surface days. And this is the higher direct cone, this is the lower direct cone. And then there are gap in between. So because of the structure, you can imagine we can walk down by looking at the constant energy contours. You can take slices of this horizontally as you lower energy, right? So here right in the middle, I can right in the middle around this energy, if you're slicing across here, the pair outside are hole-like, and the thing pocket you have in the middle will be electron-like.
Oh, okay.
So this is where you can realize this situation.
Okay, because they all look bulged out. That's why I was now a little confused.
Yeah.
Okay.
Yeah.
Got it. Thank you.
Yeah.
I actually have a question, Ming. If you go to slide number 40, I'm a little bit curious about how we define a gap versus gapless, or maybe a slice above, like 39. I want to see
This one.
Yeah, exactly, right here. So if we compare D to C, where you define gap versus gapless, right? And the D even have less intensity compared with C.
I see what you mean. Yeah, that's a good question. So basically this set of EDCs is right, they're taken like this. The red one is in the middle, and if you have no gap, you would expect a single peak there.
Okay.
So this high intensity here is from this bulk states. We can ignore that. We just focus on this part.
Right. I see.
And then for this one, if you follow in the middle, and if you follow the peaks, right, as you go towards the red one in the middle, this is consistent with two separated peaks with the gap in between.
Right. I got you. So the gap will define the between those gaps, those peaks. Those single peak.
Only strictly talking about the surface state. So this is the bulk band. So this is the bulk band. We don't. Yeah.
Okay, got you. Thank you.
Yeah.
Do we have more questions from the audience? All right. If not, maybe we should move